Good morning, everyone. So, in the last class, recall that we introduced linear transformation, which is a map from T U to V. Now, the larger aim is to see that under what condition U and V are isomorphic. So, a function is isomorphic. Two sets are isomorphic if the defined function is 1 1 and on 2. Similarly, we need to check that T is 1 1 and on 2. To check T is 1 1 and on 2, we need the concept of kernel and range of a linear transformation. So, kernel of a linear transformation is defined as the set, or it is a subset of V where the images of all the vectors is the 0 vector of W. So, all those V in capital V such that T of V is equal to the 0 vector, and the range is defined as T of V such that V belongs to capital V. So, range of T is a subset of W, while the kernel T is a subset of V. Even we will see that kernel T forms a subspace of V and range T forms a subspace of W. So, let us see some quick examples. Recall the zero transformation which takes all the vectors to the zero vector. T is from V to W such that T of V is equal to 0 vector. Yes, we need to find the kernel and range of the zero transformation. So, kernel T is all those vectors whose images is the 0 vector. Now, for the zero transformation, image of all the vectors is the 0 vector, and therefore the kernel T is capital V. The range T is T of V such that V belongs to capital V. So, now T of V is the 0 vector, it is already given, and therefore the range T is the 0 vector. Identity operator is defined from V to V such that T of V is equal to V. So, kernel T is all those vectors for which T of V is 0. Now, T of V is 0 and T of V is V, which means V is 0, which means the kernel T is the 0 vector, and range T is all T of V for which V belongs to capital V, but T of V is V itself, and therefore the range T becomes capital V. Determine the kernel T and range T for the following transformation where T of x is equal to A of x. So, if I write down the kernel T, then it is all those x for which T of x is the 0 vector. Here 0 vector means the 0 vector of Rm, and it means all those x for which Ax is equal to 0. Yes, now if you relate the concept of the column space, row space and null space, then this is the definition of null space of A. Yes, which means that null space was associated with matrix only, while the kernel T is the generalization of the concept of the null space. Similarly, if I define the range T, then range T is all those Ax for which x belongs to Rn. Yes, now try to visualize what is range of T. Now Ax, if I write down the columns, then the column is A11, A21 and so on, x1 plus A12, A22, so on, x2 and A1n and ANN, xn. This is my range T, which is the linear combinations of the columns of A, and therefore the range T is column space A. Let's see the next question. T of P3 goes to P2 such that T of P of x is equal to P dash x. So if I see kernel T, then the kernel T is all those P of x for which T of P of x is the 0 vector of P2. Yes, so all those Px belongs to P3, which is A0 plus A1x plus A2x square plus A3x cube, such that P dash x is equal to 0. Now P dash x is A1 plus 2 A2x plus 3A3x square is 0 plus 0x plus 0x square. If I compare the coefficient, then it gives us A1 is 0, A2 is 0 and A3 is 0, and therefore my kernel T is A0 such that A0 belongs to R. Now this can be written as span of 1, where 1 is a polynomial, which means it's a vector. Therefore the dimension of kernel T is equal to 1 and its basis vector has only one vector, which is a non-zero vector, which is 1. Now it's easy to write down the range T here. So R of T is T of P of x, which is P dash x. P dash x is A1 plus 2A2x plus 3A3x square, where A1, A2, A3 belongs to R. And this is a span of 1x x square, which means the range T is equal to P2. So its dimension is 3. One more quick question. So M22. So kernel T is all those vectors A11, A12, A21, A22 such that L of A is equal to 0. So which means A transpose is equal to 0. If you take A transpose, then it becomes, this should be the 0 matrix. It gives you all coefficient to be equal to 0, which means the kernel T is the 0 matrix and its dimension is 0. If you see the range T, then it is A transpose, which is A11, A21, A12, A22, where each Aij belongs to R. Its dimension is 4. T of xyz is equal to 0i. So kernel T is all those xyz for which T of xyz is the 0 vector of R2, which is 0, 0. So this gives me all those xyz for which 0, y is equal to 0, 0, and this implies that y is equal to 0. And therefore my kernel T becomes x0 z such that xz belongs to R, and I can write it as span of 1 0 0 and 0 0 1. We have discussed it many times. You can try it by yourself also, and both are linearly independent vectors. Therefore dimension of kernel T is equal to 2, and range T is 0, y, where y belongs to R, which is span of 0, 1, and therefore dimension of range T is equal to 1. You can also observe in all the examples that dimension of kernel T plus dimension of range T is equal to the dimension of V if T is a linear transformation from V to W. Now kernel T is a subspace of V. Please do try to solve it by yourself. It is not difficult. So to solve it, let us say that U and V belongs to kernel T. I have to show that U plus V and KU belongs to kernel T. So u plus u and v belongs to kernel T. It means T of u is equal to 0, T of v is equal to 0 vector. Now T of u plus v, using the definition of linear transformation, becomes T of u plus T of v, which is 0 plus 0, which is 0 vector, and therefore u plus v belongs to kernel T. Similarly, you can show that ku belongs to kernel T, and therefore it is a subspace of V. Now range of T. So range of T, now T of u and T of v belongs to R of T, which means u and v belongs to capital V. Yes. Now I have to show that T of u plus T of u plus T of v belongs to range T. So T of u plus T of v, which can be written as T of u plus v. Yes. Now uv belongs to capital V implies u plus v belongs to capital V. This implies that T of u plus v belongs to range of T. Similarly, try to show that T of ku, which is k times Tu, belongs to range T. Yes. So in this case, range T is a subspace of W. Now if T is a linear transformation from V to W, then the dimension of range T is said to be rank T, and dimension of kernel T is defined as nullity T. So this is a simple question where we need to find the kernel T and range T, and then the basis for kernel T, range T, and their rank and nullity. So kernel T is all those x, y, z where T of x, y, z is equal to 0, 0. Now this gives me x is equal to 2y and z is equal to minus y. Also you can see that x minus 2y is equal to 0 and y plus z is equal to 0 is a homogeneous system of equations where there are two equations and three variables. It means there must be one free variable, and therefore kernel T becomes 2y, y minus y belongs to R, which is span of 2, 1 minus 1, and therefore nullity T is equal to 1. If I find the range T, then I can write it as x times 1 0 plus y times minus 2 1 plus z times 0 1, which is span of 1 0 minus 2 1 and 0 1. Now you can easily observe that the set is not linearly independent because minus 2 1 can be expressed as a linear combination of 1 0 0 1, and therefore this becomes a span of 1 0 0 1. Recall the theorem that if V can be expressed as a linear combination of other vectors of set S, then span S is equal to span S minus V. Now 1 0 0 1 is linearly independent set. It forms a basis of R of T, which is 1 0 0 1, and therefore dimension of R of T, which is rank T, is equal to 2. So I have added the solution in this slide also. One interesting question is, consider the matrix transformation. So here matrix transformation means T of x is equal to Ax, and we need to find the rank and nullity. Now rank and nullity means that we need to find the null space of A and we need to find the column space of A, for which first we need the RREF or REF. If I compute the REF, then there are three pivot entries are there, which means the rank A is equal to 3. Yes, and there are 1 2 3 4 5 variables are there. it gives us the homogeneous system of equation where 5 variables are there. 3 are dependent variable, 2 are free variables. So number of the free variables gives me the nullity A, which is 2. Since I don't have to find the basis, if I have to find the basis, then I have to see that the column 1, column 2 and column 4 forms a basis. So column 1, column 2 and column 4 forms a basis for the column space. And similarly, we have already discussed how to find the null space. And rank and nullity can be directly concluded without computing the basis, depending on the number of the free variables and number of the pivot entries. This question we did where we have shown that it is a linear transformation. Now we need to find the kernel T. So kernel T is all those xy for which T of xy is the 0 vector. Here we need to identify what is the 0 vector. So for the 0 vector I must choose A is equal to 0. That gives me 0 vector is minus 1 comma 2. This is the only trick which we need to remember. The most common mistake is that we may write 0 vector as 0 comma 0. So now all those xy for which T of xy, which is 2 dot xy. Now 2 dot xy means 2x plus 1 and 2y minus 4 plus 2, which is 2y minus 2 should be equal to minus 1 comma 2. So this gives me 2x plus 1 is equal to minus 1 and 2y minus 2 is equal to 2. Solving it further, x is equal to minus 1 and y is equal to 4 by 2, which is 2. Therefore it becomes minus 1 comma 2. Now minus 1 comma 2 is the 0 vector of the given vector space. Therefore nullity T is equal to 0. Again you may do a mistake. You may consider minus 1 comma 2 as a non-zero vector, but it is a 0 vector and therefore nullity is equal to 0. Now in the case of the column space, row space, we already did this theorem. Now this is the generalization where n is the dimension V. So please do remember it. Rank T plus nullity T is equal to dimension V, where T is a linear transformation from V to W. So this is the last question where T of E1, E2, E3, E4 are given, where E1, E2, E3, E4 forms the basis vectors or the standard basis of R4. To find the rank and nullity, first we need the given linear transformation. So in the last class we did a similar question where we found the given linear transformation. In this case it comes out to be T of x, y, z, w is equal to x plus y plus z plus w, comma x minus y, comma x plus y plus w. Now if I have to find the kernel T, even I am interested in nullity and rank T. So kernel T is all those x, y, z, w for which T of x, y, z, w becomes 0, 0, 0. This gives me 3 equations. Now here we have 3 equations. It's a homogeneous system of equation with 3 equations and 4 variables. It means 4 minus 3 free variables. It means nullity T is equal to 1. It means rank T is equal to number, the dimension of R4, which is 4 minus 1, which is 3. Okay, so that's all from today's class. In the next class, we'll introduce the concept of 1, 1 and on 2. Thank you very much.